Hello everyone, welcome to our engineering failure analysis, Project 1 with Andrian, Miguel, and Marvel. So our case focus on a premature failure in the transmission system of a Formula SAE racing car. The half shaft, which connects the differential to the wheel, was expected to last 500 kilometers. However, it fractured after only 100 kilometers of use. The failure occurred under high torque, right as the car was accelerating out of a curve. This unexpected event immediately raised one critical question. What exactly caused the shaft to fail so early? So the fail component, as you can see, in this case was the transmission half shaft. Its role is to transfer torque from the differential to the wheel hub, allowing power from the engine to reach the ground. At both ends, constant velocity or CV joints allow for smooth angular motion. The shaft itself has splines cut at both ends, and these splines are where torque is actually transmitted. The critical location and ultimately where the fracture occurred was at the spline root, a geometric transition that naturally creates high stress concentration. So the half shaft was not only carrying torque, it was exposed to a combination of complex loads. The dominant load was torsion, of course, coming from the transmission of engine torque. On top of that, bending stress act during cornering and from the vehicle's own weight. And finally, shock loads appear during aggressive gear shift or road impacts. These loads were not static, they were cyclic and constantly changing. The cyclic of torsional and bending stress create the perfect condition for fatigue to develop over time.
When we compare the actual material to the specified one, the cause became much more clearer. Where the design is required to be AISI 4340 steel in a quench and tempered condition, and this has a high yield point and very excellent fatigue resistance. Instead, the shaft was manufactured from normalized AISI 4140 steel, and its yield strength is only about 665 megapascal. And compare this to the 1110 megapascal of the specified alloy. Now, similarly, its ultimate strength is also much lower. Uh, and if we look at the microscopic level, the 4340 would have been formed and tempered from martensite structure. But 4140 only produced a benitic structure with weaker mechanical properties. So this material mismatch meant that the shaft simply could not withstand the stress that it was designed for. Okay, now the failure of the half shaft can be broken down into three stages. First, the cracks is initiated at the spline roots, where the stress concentration is at the highest point, and in this case that the stresses exceeded the yield strength of the material. And the next, we have under-repeated torsional loading, where these cracks slowly propagated. Uh, and this is a classic fatigue process. Finally, once enough of the shaft's cross-section was consumed by the cracks, the remaining ligament could not sustain the applied torque. Now, at that point, the stresses exceeded the ultimate tensile strength, and this caused the rapid overload of this overload fracture. And this is confirmed by the twisted splines seen on the fracture surface. We have some microscopic evidence where the analysis shows that some kind of failure sequence that confirms our analysis. So the optical micrographs revealed multiple cracks originating from the spline roots, where the concentration is highest, and secondary cracks is also observed along the spline surface. And at higher magnification, SEM fractography gives us like a dimple morphology, which is a mark of ductile overload. Now, together, these microscopic features confirm that the shaft first failed by fatigue, crack initiation, and propagation, and then fractured completely by ductile overload. When we evaluate the results against stress strain limits, the evidence is clear. The effective stress at the spline root exceeded the yield strength of the actual material, and this triggers the plastic deformation and crack initiation. Over time, the endurance limit of the material was not sufficient to withstand the cyclic torsional loading, and this leads to fatigue propagation. Um, and finally, during a high torque moment, the applied stress surpassed the ultimate tensile strength, and this caused the catastrophic ductile fracture. So, in other words, every critical material limit, namely the yield, the fatigue, and ultimate, was all exceeded and explains the premature failure.
Okay, now the first and the most important preventive measure is strict compliance with specified materials and heat treatment. The shaft should be made from AISI 4340 steel in quench and tempered conditions, as originally designed. To ensure this, routine checks of microstructures, hardness, and tensile properties should be carried out as part of a rigorous quality control process. If this had been done, the yield strength would have been raised above 1100 MPa and the ultimate strength to nearly 1300 MPa, providing a much larger safety margin and significantly improving the fatigue resistance of the shaft. Next, beyond the material choice, the design itself can be optimized to improve durability. One key improvement is to increase the fillet radius at the spine root, as the provided picture here, where it compares for each radius for the spline, which reduces the stress concentration factors and lower peak stresses in the region which is critical. Another proven method is shoot pinning, which introduces compressive residual stresses at the surface. These residual stresses counteract applied tensile stresses, making it harder to fatigue cracks to initiate. Together, these two measures can significantly extend the fatigue life of the half shaft. Lastly, additional measures can be taken to further reduce the risk of premature failure. Ensuring that the splines are properly fitted and well lubricated minimize fretting wear, which can otherwise accelerate crack initiation. In addition, applying non-destructive testing method such as magnetic particle inspection or dye penetrant testing allows early detections of crack before they reach a critical stage. These preventive measures add an extra safety margin to help ensure reliability during racing conditions. So, in conclusions, the premature failure of half shaft was caused by combinations of using the wrong materials, which normalized using AISI 4140 instead of quench and tempered AISI 4340, and the stress concentration at the spline roots. This set a clear failure sequence: fatigue crack, initiations, crack propagations, and under cyclic torsional loading, and finally a ductile overload fracture. So the lesson from this case is that we must ensure the correct materials and heat treatment, and then optimize the spline design and surface conditions, and lastly, then maintain rigorous quality control inspections. This case demonstrates how applying stress strain principle directly prevents real-world engineering failures, especially in high-performance applications like Formula SAE racing. Thank you.